it's going to be an interesting talk, I hope. I'm going to talk about an area that is not quite my field of expertise, in the sense that it's a model of partial differential equations that I'll be talking about. And that's joint work with Chris Hassan, who's now in Cork, and Claire Postlethwaite here in Auckland, and Alistair Ruckledge in Leeds. And so Alistair is, of course, the PDE specialist here, and Alistair and Claire have been working on what is called a heteroclinic-cycle model that I will be introducing soon. And the work I'm presenting is stuff that we did, the four of us, with when Chris Hassan was a postdoc in our department. And he did two different things. I specifically am going to talk about the periodic traveling waves. And so hopefully I will explain the meaning of the picture on this slide soon. Okay. So I want to start with the bicycle riddle. It's just to keep your minds busy in case you think that you're getting a bit bored by some of the equations that I'll be showing, or so you can wonder back at how this one works. Just imagine there are three bicyclists and they have exactly the same route to get to work. They are biking, well, maybe the fastest they can, or you know, there's a certain competition going on here. And we have this first bicyclist, going the wrong way. And so let me call this bicyclist Ruckledge, who's really, really fast bicyclist. But then there's this other bicyclist, Postlethwaite, and more often than not, Postlethwaite actually arrives at work before Ruckledge. And the third bicyclist, you know, that you could say that's cheating, perhaps. That's a tandem setup, and you know, I had to merge the names a little bit. So let me call this tandem pair Singh Hassan. They're very good. They actually more often than not beat Postlethwaite to arriving at work. And so the riddle now is it possible that more often than not, Ruckledge is faster than Singh Hassan? And well, you need to give this one some thought, perhaps, or maybe you've heard the riddle before. I'm just going to give you a small hint that by the choice of names is perhaps also clear. There is a game that people play, which is called rock, paper, scissors. And I'm also assigning colors here. Rock is red, paper is green, and scissors are blue. And maybe now you know the answer of the riddle. Just in case you find this a bit sort of like, well, what is this? I thought this was applied mathematics talk. And so here is the actual application that we try on our, if you want, our grant proposals, and to get certain papers past referees. So there is actually in ecology a situation that is considered more and more of interest, that there is a certain cyclicity in which species has the dominant hand, if you want, or the advantage. And the most famous example is actually of three different lizards that where the male lizard has different colors even, and so you can see which population species has the dominant hand. You have an orange one, and well, okay, you know, we consider this orangey, and then there is a bluish one in terms of what the chin or the throat is colored like, and then there is a yellow one, and it really is like this, that the species, if you look in populations where they're growing in California somewhere, if you count them, then in certain years there are lots and lots of orange ones, and then in other years there are lots and lots of blue ones, and yet other years there are lots and lots of yellow ones. And this is, well, I have here the quote on the Wikipedia page: the behavior is very much like rock, paper, scissors. there is the, how does it go? The paper wraps rock, scissors cut paper, and rock, I forgot the word now. There's something that the English say, that the rock is making the scissors no longer sharp. I forgot the word. And so, well, it's a game that apparently is paid a lot. I'd never heard of it before I started this research with Claire and Chris and Alistair, and or maybe I should say with Rutledge Postlethwaite and the other half of Singh Hassan. It's an interesting ecological setup, because you have no winner takes all. There is no best species. There is a certain periodicity that you could observe in this evolution of species. And so there is, if you want, a nice coexistence, but it's not that at any one time there is an equal population of all of these different lizards. There's a coexistence that has a time component as well. And so this is the sort of motivation for these kind of models, where they specifically build in the this cyclic competition. And so the equations that we work with are very simple kind. There are three particular ones, and rather than calling them R, P, and S, as I did in the beginning, I'm going to call them A, B, and C, which is mathematically perhaps a little more acceptable. And then the colors are still red, green, and blue. So the equations you see here on the bottom give you this sort of, there's the ODE component here, which is symmetric. There is always a part where there's a zero equilibrium state, if you want, that occurs. And then the other steady states, you can sort of read off to some extent that if B and C are both 0 and A is 1, then that term here is also 0. So there are additional equilibria on coordinate axes. And then there is this coexistence equilibrium, if you want, that has a particular formulation. And you will see the equations a bit later on a different slide. And so what we are interested in is more, not so much the commuting riddle, where these equations would be enough, but thinking about population species as they are distributed over some landscape. And since I'm interested in, or I'm talking about periodic traveling waves, it suffices to think just in terms of a single spatial variable. And so I'm adding a diffusion of these species, in that they might, just interact with each other. And this is on a single line here, because of my interest in the periodic traveling wave. So in space, these would similarly be on, if you want, you can think of polar coordinates, that you have these rings, like throwing a stone in water and getting these rings ripple out. And so you see a picture, and the picture is well, calculating with the demonstration that I will show in a minute, and the actual computations are done in a coordinate frame of the traveling wave. And so here you see this coordinate x plus gamma times t, where gamma is the wave speed. And if you rewrite the equations in this coordinate x plus gamma t, which we call z, then the actual equations change almost not at all at first glance. I mean, just look at it. ddt gets replaced by gamma d dz, and the d squared dx squared gets replaced by, that should be a d squared dz squared in all three rows. I apologize for the typo. But now I have got dependence only on the single variable z. So I've turned my system of three partial differential equations into a system of three second order differential equations with respect to the traveling wave coordinate. And so within that space, I can look for steady state solutions, and the periodic traveling waves are actual periodic orbits in that space. And so here I see the same traveling wave that I had in the previous picture, but now plotted in the ABC space, where you see it calculated as a periodic solution. So that's this black curve here, and the way I'm going from the A axis towards the B axis, towards the C axis, and back towards the A axis. And that's the periodic orbit that exists for these parameters, sigma 3.2, zeta equal 1.0, and the wave speed gamma at, well, some strange value if you want. Why is it gamma this strange value? So what has happened is I've picked up the periodic traveling wave that corresponds to a periodic orbit in this system of ODEs that has a period of exactly 20. And so I was talking about the coexisting equilibrium already, when all the coordinates have actually the same value, and it's the value 1 over 3 plus sigma, and so that you can see that's some number between 0 and 1, and that's the point that you see here. Now, the on-axis equilibria, I've given these colors. So when A is truly dominant, there is no B and C, we have a red point. And when B is truly dominant, there's no A and C, it's the green point. And similarly, when C is truly dominant, I have the blue point. And when you do the analysis of the system of ODEs, you find that there is a heteroclinic connection from each of these equilibria to the other ones. And so the direction is that from A, there is a connection to B, and then from B, there's a connection to C, and from C, there's a connection back to A. Now, of course, the existence of such a heteroclinic cycle is induced by the fact that I have these invariant subspaces because of the symmetry in the equations. And so we're well aware of that, but still we stick to that framework because that in the symmetric system, this heteroclinic cycle is persistent. So there you can perturb within the symmetry class, and this heteroclinic cycle persists. So what can I do here? This periodic orbit I've calculated with a particular wave speed, and I can vary this wave speed and choose a different one, which is directly related, if you want, to the total period of the periodic orbit in this system of ODEs. So if I have a very large, okay, maybe I should say that too, for those who are not aware of it, the period of this periodic orbit, that would be the associated wavelength, because that's the actual time for the variable z to become periodic. And so if I have a very large wavelength or associated very high wave speeds, that is associated with a very large period in a system of ODEs. And that means that I'm going to be very close to this heteroclinic cycle, because the heteroclinic cycle has infinite period. Well, actually 3 times infinite if you want to be very precise. So I have this periodic orbit here that in this picture already looks to be quite close to the heteroclinic cycle. And I actually have a whole family of periodic orbits with varying wave speed, so I can parameterize by wave speed if you want. This family goes all the way up to this heteroclinic cycle. And so here is a bifurcation diagram where now I've fixed the variables sigma to 3.2, and actually for the whole duration of the talk, it'll be 3.2. And then this variable zeta is still a parameter. And now the second parameter is my wave speed gamma. And so what you see here is a picture of the bifurcations that occur in the system of ODEs. So the system in traveling frame coordinates. And there is actually a Hopf bifurcation, and that's where this coexistence equilibrium becomes unstable, and that gives rise to these periodic solutions. And well, okay, it becomes unstable. Maybe I shouldn't say it that way. It gains additional unstable eigenvalues. So it undergoes a Hopf bifurcation, let's leave it at that. And then there is, well, actually, technically there are different types of heteroclinic bifurcations. That's where these heteroclinic cycles live. So these are particular solutions that exist only for specific wave speeds, depending on the variable of zeta that you choose. And so the point or the solution that I showed you, where zeta was equal to 1, that's roughly that big blob over here. That's where my my solution lives at the moment. And I can see, you know, I'm, well, maybe with respect to the wave speed, I'm bang in the middle between the Hopf bifurcation and the heteroclinic cycle. And so let me remind you of that picture. I'm actually, you know, quite close to that boundary already. So this is all research, that's sort of the motivation, if you want, for the talk that Claire Postlethwaite and Alistair Ruckley's already worked on a couple of years ago, and that didn't involve me nor Chris. So the actual interesting part that we contributed to this is, what about the stability of this periodic traveling wave? And there is something peculiar about it when you consider this setup with the heteroclinic cycle, because if you think about how you would consider a perturbation arising in your system, then what would happen to it as time evolves? Well, if you're close to a heteroclinic cycle, you're going from one equilibrium solution to another in the ODE. In the PDE, that is there's a front that travels, and that would be you would expect that to be unstable in the PDE context. So any perturbation, you should grow. Now we have 3 of these together, and so we have 3 unstable, if you want, fronts connected together in some circular manner. And what we found is that actually that makes creates a possibility for this periodic traveling wave, so this cycle of 3 unstable fronts, to be stable. And so I guess that's the main message of this talk in terms of the theory, and in terms of the topic that I really want to focus on is, can you compute that? So, okay, this is what I just kind of said. If I have the 2 on-axis equilibria, they are, you know, if you do the stability analysis, you expect this front to be unstable. But if you connect them together, we find that as long as you have a large wavelength periodic traveling waves that are very close to the heteroclinic cycle, then they turn out to be, they can be stable. So it's not easy to compute this in the context of this particular example, and more generally in the context of an example with heteroclinic cycles, because the system setup doesn't like stuff hanging around a coordinate axis for a long time, for example. And so I'm in the periodic traveling wave is changing from being close to the equilibrium at the on the a-axis to moving swiftly to the equilibrium on the b-axis, and then moves on to the c-axis again. And so you're changing from values 0 to 1 very rapidly. So there is a stiffness in the system that's inherent in these heteroclinic cycles, but also you're changing to values that are order 1 to values that are really 0. And numerically, that is quite challenging. So the setup that we use is, and that, you know, what I specifically want to stress is that we are using to compute the stability of this periodic traveling wave, we are using an approach that is well known, and that's, well, you know, even if you don't do PDEs, probably you know about this. I don't know, I'm not sure. I certainly already knew that that Björn Sandstede and Scheel have been working on this for a long time, and the paper by them and Jens Rademacher from 2007 gives a very clear and detailed overview of computational techniques that are needed for periodic traveling waves. But in their setup, they don't worry about these zeros and ones and heteroclinic connections and stuff. So they do normal ones if you want. And so what we have done is formulate the equations in terms of logarithmic coordinates. So instead of taking A, B, C, we're taking the log of A and the log of B and the log of C. What happens that way is that if the log is 0, you're 1, but then to hang around 0 is drawn out into the whole negative axis. And so we get easier transitions to go from between 0 and 1, because we're now going just down into along the negative axis and back again. And so what I want to specify a little bit more detail is how we scale the associated eigenfunction to find whether you've destabilized or not. That scaling needs to be done in the right way within this logarithmic setup. So that's not trivial. And so I want to show you a few equations, and hang on. Yeah, okay. I thought I had a mildly less filled slide in between here, but there's still something missing, so more is coming. But here is the setup the way you would expect it. So in U coordinates, I have these first two equations. That's just my system of second order differential equations written as a double the dimension, so 6-dimensional system of first order equations. And so the first component, that's just the derivative, and then the second component that gives me the derivative of the derivative, and that's my my partial differential equation, the way the ordinary differential equations that we have seen earlier on the slide. But now ABC thought of as being some big vector U, and this complicated population interactions that is all captured by that function f. And so the second part, so the equations for V, that's taking the linearized system. So you take the linear operator that you get from this ODE and set up a first variational equation where the vector V plays the role of eigenvector that is, well, Z dependent on the solution U, which is the periodic solution. And so again, this is done in a second order system. So the first component is just a derivative, and then the second component gives you the linearization of the equations. And then the lambda V here tells you that you want this to be an eigenvector associated with the temporal, that would be the temporal eigenvalue lambda of this operator. And so, of course, and I didn't put that down, there are periodicity conditions necessary to make sure that U is a periodic solution. And there is a phase condition, if you know what that is, to make sure that you have a uniquely defined periodic solution for your parameter setting. And then the vector equation has additional boundary conditions that tell me essentially that I want V to be an eigenvector. So once I've gone full circle, I want the eigenvector to lie in the same direction as when it started. And so after one full period, I want this eigenvector to be in the same direction. But the way we set this up, and this is again from Rademacher and Sandstede and Scheel, is that this eigenvalue, so the actual contraction rate, that is now associated with the spatial component. And so the spatial component I want to keep on as a unit. So yes, I'm allowing rotations, but only with length, that the length remains the same. And so you set this up with this, if you want, the spatial eigenvalue in the form of a root of unity. Now, I want all of this in logarithmic coordinates. So I'm going to define a W that is just the logarithms of all of this. Now, if you think about this, if I take the logarithm of A and now I want to know what is the dz of A, then that would be now I need to take the dA of the log of A and then the dz of A to get the component for W. And so I put here, note that if you take the derivative of U, so this derivative, that is the same as taking U times the derivative of Z. Yeah, that's because the logarithm is 1 over A, for A, for example, it's 1 over A times the derivative of A. And I put that over on the other side so that I don't need to put a fraction. But this is essentially the change. And so you see that there's a factor U in here. And now if you take the derivative of this again, you're getting what's the multiplication rule? So you're getting the derivatives of U and you're getting the second derivatives of Z and these multiply together. So the equations look deceivingly similar if we compare the U equation upstairs with the equation downstairs here, except that I now conveniently wrote a G instead of an F. And so this function is saying, okay, take the exponential and then the inverse exponential at the other end. So first you take the exponential, then you calculate the F, and then you take the inverse exponential again. So that's done here to change the U coordinate to W. But I'm also getting this square component here of the derivative WZ. And that component is there because of this product. Okay, so if you work out the details, that pops out. Now, that's the first part. This is the setup actually for which we calculate the periodic orbits. Now, if we want the stability, we also need to set up the first variational equation. Now, I ran out of, I don't know, UVW, what comes after that? So, so I'm going to call this vector V again, but it's now a V in logarithmic coordinates. And so this is the equation that you get for the V component in terms of the logarithmic setup, where you know, you want this now to be in logarithmic coordinates. And the nice thing about this is that you're getting a setup where the phi, this polar or phase coordinate, phi is appearing in the equations, and instead the boundary conditions, it has disappeared. Okay, so now in this particular case, I have periodicity only when phi is equal to 0. Here, I have a nice periodic eigenfunction for any phi. So that's actually quite nice. Okay, now, the whole reason that I'm sharing the screen is because I want to show you this computation. And so I've got it set up that if I hit run, auto will start. So I also timed it, and I have learned from experience that if I try that, then it's a lot slower over Zoom. So this is the scary part. I'm not sure how long it'll take. So this is the moment where it starts hanging on my normal without Zoom. This takes at most 30 seconds. But I have a bit more time, I think, now. So here, what has happened is I've set up my system. And as you see, there's this HB here. So I started from the coexistence equilibrium, which I happen to know exactly for my value sigma equal 3.2. It's 1 divided by 3 plus sigma. I am receiving a chat. The Zoom calls X or MX. Oh, yeah, Andy, you know too much. I'm ignoring these IEEE overflow flags, and I think a lot of people do. It's not, I'm not sure where they come from. It's probably some implementation thing. I'm not going to try explain it, but they have no effect on the accuracy of these computations. So I hope you don't hear my computer now starting to make a lot of noise because it's working hard. So I have my Hopf bifurcation detected. And now I'm picking up the Hopf bifurcation. And so that happens in step 2. And I continue. And as you see, my continuation is in this parameter, gamma, which is the wave speed. And as I change gamma, I also change the period. So the two are related. And as you see here, there is the period 20, which is the user specified point that you see coming up here. And so I'm detecting it and I continue on so that I get also some even closer to the heteroclinic, but we start with period 20. So now taking that period 20 orbit, I'm setting up an extended system, which is really that now I have my system of equations that was formed by the U components, or better, the W ones, the logarithm of U. And I now take the extended system where I add the linearized system to set up the eigenvalue problem. And so to do that, of course, now you have a vector setup where your vector could have any length. And so we're setting it up so that the eigenvector, eigenfunction that is associated with my system initially has, it has a total integration norm of equal to 1. And so that's just, you start from the zero bundle if you want, and then you go until the norm is 1. And so that's what's happening here. That's a very quick step. And then when you continue, we have the continuation of the essential spectrum for this parameter value. And we are seeing here that now we are following this in, there is the real value of lambda, there is the imaginary value of lambda. So that is my temporal eigenvalue. And then I have my phi, which is the phase of the point on the unit circle that is associated with the spatial eigenvalue. And there are two directions, right? I go in one direction and then the opposite direction. And so apparently, wrong one, sorry. No. I should get this. I have a lot of stuff open, and my apologies. So the pictures popped out, and let me show you first the picture on the left. What I have here is, you can't quite see it, but that's the real part of lambda, and I have the imaginary part of lambda. And where I started, I didn't quite say that, but at phi equals 0, there is the eigenvalue lambda equals 0 is actually a solution. It is exactly the tangent bundle of the periodic orbit. And so we know what the tangent bundle is. That's just given by the right-hand side of the vector field. So this is our starting point. It's a bit tricky because, as you see, it's where we have a vertical tangent on the branch, but this works well. And this is also already noted in the work by Rademacher et al. The thing that they seem to overlook is that you can just fill in the right-hand side. That's something that we are, that's our starting point. And so there is a fold detection, and then the real part of lambda just goes off into the negative half of the complex plane. And in this second picture, you're seeing the solution, which is now the logarithm. And so you may remember the picture that I showed you on the slide, my first slide of the wave solution. And so here you see the wave solution for one period. Maybe I shouldn't call this T, that should be Z, but it's not really Z either because it's scaled. So the actual period is scaled to 1. And what you're looking at is, well, not quite red, green, blue, but it starts with green here, green, blue, red, but in logarithmic coordinates. So it looks a little bit different from the picture you saw before. Most importantly, my maximum is now 0. I'm not even that close to 0. And then my range is to about -6, which would be e to the -6. That's quite a small number. So I do get quite close to 0 in this zeta setup. Okay, now in the interest of time, I'm going to start the calculations for the actual onset of the instability. I've learned that that's a good idea. Then I will have the stuff pop up while I get to it on the slides. So I'm going to hit start here, and let's hope that that goes well. My computer will, of course, start screaming that it's hot and things like that, but hopefully we will survive and I won't have a screen freeze or something. So this is the picture that I showed you with a little bit more detail, and now at least you can read it. It's the real part of lambda and the imaginary part of lambda. So I have now here a relationship between when the temporal eigenvalue is such that the spatial eigenvalue has reached modulus 1. And so anything inside here that has, there's no spatial growth at all, everything dies out. And so if now the temporal eigenvalue is in the left half of the complex plane, then everything's fine. So the moment, even if lambda is in the left half of the complex plane and I go outside, then of course there is a spatial growth that will just explode. And so there's an instability in the spatial part, if you want. But what I see here is that I have a part of my lambda values on the boundary of the spatial eigenvalue that is in the positive half. And so this particular traveling wave, periodic traveling wave that corresponds to these eigenvalues, parameter values with a wavelength equal to 20 is actually not stable. Another thing maybe to point out that I start with phi equals 0, and you have this this phi is like an angle. So when I reach 2 pi or minus 2 pi, the whole thing repeats. But since you remember that was in the equations as just a minus I phi, that has a different lambda associated with it. And so I will continue to follow this curve into the far negative half of the complex plane by letting phi grow bigger and bigger and bigger. And then, of course, because I'm in the real space, I would expect that this is nicely a symmetric eigenvalue picture. Okay, I hope you can't hear the noise of my machine because I can barely speak over it. So, well, great, the thing is unstable. So now what do I do? Well, I can change my, my wavelength and associated wave speed. And then I will hopefully reach some stability in the sense that my entire essential spectrum will lie to the left of the imaginary axis. And as you see here, this happens in some sense counterintuitively, perhaps, happens when your wavelength goes up. Maybe I should say a little aside here that the only instabilities that we have found are the ones that I'm showing here, namely that if you want these two folds merge with the fold in the opposite direction, and so you have a higher order tangency at 0, then you would normally, so this is a quadratic tangency, and this one would be the fourth order tangency. So because of the symmetry, of course, the cubic one is not there. And so you can think of that as a curvature, loss of curvature at that point. And so we can just calculate that by imposing some restriction or a condition on the eigenvalue lambda, so on this branch, relative to my I phi coordinate. And so this is a bit different from how this is implemented in other packages. The way we do it really is worked out in detail by hand, if you want, and then implement it. But we found that this works very well. So you could, I guess, if you're an auto guru, you would think like, oh, you just follow the fold of the fold, but it doesn't. That does not as stable as having it implemented hard-coded or hardwired like this. Okay. So I think I should now be ready with the computations. Maybe let's try this first. Oh, I haven't spoken long enough yet. So, well, maybe I will talk about it anyway. So when I have set up my my eigenvalue problem, what we are doing is starting from the 0 point phi equals 0, and we're measuring that derivative. And so we are detecting, if you want, as we are changing the wavelength, that we have a 0 of the second derivative, because the first one is already 0 by definition. And so that is what is happening here. There is, again, an extended system to take care of that condition of what is actually that derivative. And then in run 4b, we're detecting that 0. And I look here that zeta is, I think, oh, hang on, no, it's 1. I'm sorry, I'm getting confused here. So this lambda and lamp pp are the derivative and the second derivative that we are looking for. And so what is happening here, we're picking up that there is a 0 here of order 10 to the minus 8. And then that point gets followed in 2 parameters. And okay, here we go. So let me go back 1 sec. So we are continuing the 0 curvature point in the wave speed, and so that's in the wavelength and in a second parameter. And so again, I said sigma was going to be fixed, so that's going to be zeta. And so zeta was 1 all the time here in this run, and now zeta is varying in this run. For example, here you can see it's changed to 1.6. Now, what do we do here? This run goes all the way up until the wavelength is 100, one direction, other direction. And so let's have a look at the pictures. One picture is deliberately empty. It's part of my show. So here I get this, what we call the Eckhouse curve. And I have the wave length in the vertical axis and my zeta in the horizontal axis, which is maybe a little bit confusing from the pictures that I showed earlier. But when zeta is equal to 1, I see that at 20, that's here. At 20, I have not entered this across this curve yet. So upstairs in the curve, that's where I'm stable. And you see that there's a whole range of zeta values, but you need to have a relatively large wavelength. And just to show that in comparison with the picture that I showed you earlier, here I have my solution. And this is the solution that is at the very top of my curve. And one thing that you notice is that now I do reach 0. So I hang around at one of the coordinates, in this case, the green one, B, being close to 1. And then C is close to 1, and then A is close to 1, much closer than in this picture here. But I also see that my coordinate goes very, very much more negative. So it's, it's up to -40 in this picture, where it is only -6 here. And so even though this looks like, oh, well, I'm just touching and then I go back up already, that is where I'm pretty much 0 all the time. I'm hanging around at 0. And I can do the same thing for the solution here, which is at the fold. So it's a much lower value. And here you see even there at the onset of my instability, I have quite a large range in my logarithmic coordinate. And so I do hang around 0 quite a bit. And so I can't quite show you all these solutions in one picture, but I can show, well, maybe let me just do the 1 and 2 together to give you an impression of, you know, this is the one at the very high wavelength with the right colors. The one with the wrong colors is much lower, but still on the boundary. And then this one would be only half as deep in that picture. And so you really see here the effect of this logarithmic coordinate. Okay, and so now I think I'm almost done. So I have here a picture that is pretty much a reproduction of the picture that I just showed you from the computation, but around it I have what we call the belts of instability. And this is actually a neat idea that Chris came up with. If I go back to my previous slide, in this picture here, I can also pick up that full point at which that's like the extreme of my spectrum that lies in the positive half of the complex plane. And as long as this distance from 0 is not too far, I have only a small instability. And so Chris decided to think of that as like level sets. And as you grow towards the instability where you do not protrude into this positive half of the complex plane at all. And so in this picture, you see that if I'm going 10 to the minus 2 out, then I get this black curve here. And if I go 10 to the minus 3 out, then I start hugging that Eckhouse curve already a little bit. And 10 to the minus 4, it's even better. And so this calculation can easily be done by just following the full point in auto. So it's an easier setup, and it already gives you quite a good idea of what is going on and where your stability might lie. So if you want, it's a bit like I'm trying to find a homoclinic and I just follow a periodic orbit with fixed period but large. And so here it's like I'm trying to find the Eckhouse curve, but I'm just following a curve where my eigenvalue is just a little bit into the positive half of the complex plane, and but not too much, and then I have a pretty good approximation. And of course, you know, that's not quite the same analogy in the sense that this curve bends away, and what happens here we don't know yet, or you know, we haven't investigated much. So but it does give a much better idea of how sensitive the system is to instabilities. And we also check this against simulations. And for that, you need to look at the pictures in the paper. So to end, I guess, let me, well, wave goodbye to my bicyclists. I have, oh, I see one spelling error. I thought I caught all the travellings with one L. Sorry, there's one more. I've been talking about the computation of periodic travelling waves. And, you know, the setup is the way I hope you're used to it. You change the travelling wave coordinates, and then you just follow a periodic solution. And in this particular case, that emanates from a Hopf bifurcation. But we don't stay close to the Hopf bifurcation. We're interested in moving far away from the Hopf bifurcation towards the heteroclinic-cycle that we have built in the system because of the way there are invariant subspaces imposed. And so we're looking at the stability of these traveling waves, and we found, to our surprise somewhat, that they're actually stable if you're close to the heteroclinic-cycle. And not for all values of the parameters, but if there is a range, you have to be at large wavelength. The way to do these computations, therefore, because of the issue with the coordinate axis, as I explained, you have to take a formulation in logarithmic coordinates. And so that is a setup that works well in the context of these heteroclinic cycles, but it's also actually quite a standard approach if you have very stiff problems when it comes to the eigenvalue setup. So the variational equation in logarithmic coordinates, that's where we had the idea from. So again, I mentioned that the setup is like what's in the paper by Rademacher, Sandstede and Scheel from 2007, but we have adapted this to these logarithmic coordinates. we have these ideas of computing belts of instability instead, which is perhaps a little bit easier and more accessible. Our implementation is entirely done in Auto. I thought that was normal, especially since Sandstede is involved in it. But this is not at all the case. Jens Rademacher has everything set up in MATLAB, so which I would dare claim is maybe not that fast. Yeah, it would surprise me. So if you would like to do this in Auto, then and now you can. The Auto demo that I have just shown, maybe not quite in the same way, but a version of it is available. And so Chris Hassan put it on GitHub, and this link is also in the paper. So if you find the paper, you will find this link as well. And so you can download it and check for yourself that it is indeed quite a bit faster than while I run it over Zoom. Thank you very much for your attention.